It's a workspace file. Okay?
Yeah,
And if you have a WSP file of the same file name in the same directory as the RIV file or the RIVR file, okay, it will apply any settings, any changes that you've made from that WSP file into the river file. Okay? So maybe in the field we forgot to put in a transducer depth and we had it as 0. In post-processing we put it correct. We set it at 7 centimeters. So in that WSP file would be that change, the 7 centimeters. And if the WSP file is in the same directory, when you open the RIV file, it opens the workspace file as well. Okay, if you take that WSP file out of that directory and you open the RIV file, it opens it as it was in the field. Okay, the .riv file and the .rivr file are never changed.
So they always put in the same.
It automatically puts them in there. But if you want to take it out, or if you do take it out, you will be back to using just the raw data as collected in the field. That's it. Any questions about the setup in the field?
The most important thing is you have to set up RTK first.
Yep, saves you time. Saves you a lot of time.
And after that, you have to connect all the cable, and finally you put the battery.
And then you power it up. Again, these things are not critical. The RTK is just time saving. It doesn't matter to the operation of the instrument. It just saves you time. Okay. The cables, again, it's not. It's very rare. It's a very rare that you would have a problem, but it's just to keep things safe. Okay. Lowering the instrument down into the water, that can be difficult. And they do get damaged doing that. That's probably the antennas are the worst things. So when you lower it down, but all the rest of it is all totally watertight. So if it goes upside down, that's okay. But the antennas, then you shouldn't submerge them. They are IP. I don't know what the IP rating is. 54
or 65.
54.
No, 54.
No, higher than that. The 5 is the dust, and it might be 55, but it's certainly not 67. It's not sort of. So just be careful with those. Okay. Anything else on that, Mark?
I think one is picking the location, and the other one is preparing the day before. Because today the radios weren't paired, so we could have done that yesterday here. Pairing the radios and checking things. And
You won't have to do that again now. They are now paired. Okay, it's not
For the
something.
first time.
Yeah. To pair. And the other one was site selection.
Site selection is critical for good data. Okay, if we'd have just. We were going to do it by the first bridge. When we first turned up there, I said, right, this is where we're going to do it. And I said, well, I don't quite like it. Let's just spend 10 minutes walking around and finding a better site. Okay? Your data will go up. Quality of data will rise massively just by picking a good site. Okay. It's a great instrument, but it's not a miracle instrument. So we collected, we will look at it all in a while. We collected, as you know, data upstream and then close to the wheel, and we'll have a look at the differences, see what differences there are, and we collected it in stationary operation too. One of the things that I'm a real fan of the stationary operation software. Big. And it comes from my hydrology background as to why I like it so much. When we go across, when we have the river, and things are not great. When we go with the moving boat method, as we're going across here, we're basically dividing the channel up into profiles across the channel, as you would do, as we've done in for hydrology for years. But in the past, we've done a velocity measurement here. Now we're doing it all through the column, but we're going very quickly across. Okay, so we're spending probably maybe 1 second, 2 seconds in any one place, and the velocity distribution over 1 second is actually quite variable.
So you are talking moving boat.
Moving boat.
Okay.
Moving boat. When you use a mechanical meter, okay, I don't know how many seconds you average for here.
35.
35, okay? So if you did 1 second, you would have that. By having 35 seconds, you suddenly start to get your velocity curve. Okay, but this is almost a perfect situation. Okay? But the difference between the mean velocity curve that we've generated here and the 1 second is quite great. Okay? By going across with a moving boat, we're getting lots of sort of random. Now and again you'll get a good one.
Yeah.
Okay? And it's just purely that we're sampling so much, so quickly and everything, that we're getting the average because of the whole area that we're doing. With the stationary measurement, you will have seen, after for 1 second the data was like that,
Yes.
and after 2 seconds it was a little bit less, and eventually we came to that sort of after 40 seconds. Okay? So hydrology is Q is mean velocity times area. Okay? We're not actually doing a lot of mean velocity with a moving boat method. So that's why I like the stationary method so much. Okay, hydrology is, I'll say it again, it's mean velocity. Okay, it's not instantaneous velocity, it's mean velocity times area. Okay, and the stationary method gives you a very good mean velocity for each one, profile for each one. So I'm a big fan of that. If somebody was to come to me and put a gun in my head and say, you have got to go and collect a discharge measurement, and if you don't get it right, I'm gonna kill you. Okay? You can use any method in the world to do that. Okay? The first method I'd say is, can I have a big bucket and a stopwatch? Okay? Where I can catch it all. That's the perfect measurement. Okay? Where we capture all the water over time. Okay? It's not practical to do that out in that field. So of all the other ways that you could do it, I would choose an M9 using stationary method.
But during flight, it takes time.
Okay? Sorry?
During flight, you use stationary, it takes time.
It does. Does it take longer?
No.
We did 4 measurements. Let's say each one of them took 3 minutes.
Oh, you mean the total time?
Total time. Yeah.
Okay.
It's not that much longer. It is longer, definitely. It is longer. But let's say we took 3, 6, 9, 12, a little bit of extra time. Let's say we took 15 minutes to do our 4 measurements. Okay, if we did 15 panels across the river of 40 seconds, it's going to take us about 20 minutes. It's not that much longer. And I'm a really big fan of that.
So you prefer stationary?
I do. As a hydrologist.
Okay.
As a SonTek person, I'm supposed to say, really, moving boat is the best. Okay. So you've given me a... From the very beginning?
Yes.
Okay, so River Savannah Live, I'm using version 3.80. I believe you have 3.50 on your computers. on 3.50, you might have some, well, you will have problems with the compass data. Because we are
You upgrade the compass.
upgrade, yeah, we have the better compass on that instrument.
So,
Okay, so this is the first one you see. So I'll double click. First screen you see. It's the same as if we were out in the field. Exactly the same. If we're in the field and we're wanting to connect to the instrument, we would select the top one or Control N. To open a data file, Control and 0, Control and O, sorry, not 0. Or click on Open File.
open file.
Or, if you had recently just been working on that file, the last 4 files that you've been working on
List on.
are listed below, and you can open them from there as
Okay.
an individual file.
So,
Okay, so I'm going to open a file. By default, all of your data files are saved into My Documents, SonTek,
SonTek data.
SonTek data, SonTek data, and then on the day it was created,
Yes.
okay, it creates a folder name that is year,
Yeah,
month, day.
Yeah.
okay. I then create a subdirectory in SonTek data of River Surveyor Live, and I actually then save them in there, and I add a little bit more detail.
Photographs in there.
Yeah. So you see what?
So remember.
Put all the information.
Well, yeah, whatever that site that did, I put the photographs, I notes.
So this is by default. By default, this is where it put it. Okay. But then I sort of put it here, and then I just add Taiwan to it, or just something that helps me quickly identify.
Taiwan.
Taiwan.
It's Taiwan.
For what side?
You said Thailand.
No.
Okay. I think you're not understanding my English.
Switch to that American accent.
Okay, so when I open that up, when we open this from River Surveyor, all we will see are the .ravr files and anything that will open in River Surveyor. The .wsp files you cannot see. Okay, they are there, but the instrument's not. The software doesn't need them to open it, so they're not shown. So if you want to see whether they're there, you have to go back through. No. So if you want to see the WSP file, you would just go back here. If I went to okay, and now you see that the WSP files are there. They're actually all in there, and they link them. But actually using here, we don't see the WSP file. Only the file.
This is the reverse surveyor.
Yeah. Okay. Just want to check which files. So we're at the first site. So we did, how many did we do? 6? 6.
First one is wrong.
Yeah, the first one, there's no data in there.
Yes.
Okay, so what happened there was somebody pressed F5, the instrument started pinging, it started collecting data, it might have been in air or something like that, and they quickly aborted it. So they'd started the measurement and nothing was there. So I will just delete that one. And so these are the first 6 or 8 files that we did. So I'm just going to open all of those. At the top, you see we can click through the different files that have been opened. A quicker way to do that is use Control and T. And we can tap through all of those files. No, the Control Tab, sorry, not Control T. I do apologize. Control T is the toolbox. I'm just going to change.
Well, the old version is more scalable.
Sorry?
See, the old version is more scalable.
That's not today's data.
Oh. Oh. Yeah.
So this is all the
Okay, so I'm doing Control Tab to go through those.
Okay.
Couple of things that just you may or may not be aware of. On the Transect tab, we can only change the parameters that are shown in the top graph. Okay, and to change them, if you do a right click in the graph and go left axis or right axis, okay, you can then choose which parameter you actually want to view up there. So I've chosen the compass and magnetic error, and I've chosen the bottom track depth. You can also, if we you can change the style, well, the important thing is change the colour of the line. Okay, so if you want something different in there. And the legend position. So if that's in the way, sometimes people just take it out. If we don't like the scale, something that the river surveyor does, if we go down to the bottom, if we look at the velocity contour plot at the bottom, if I do quickly scroll through Control Tab, okay, sometimes we get lots of reds in there, okay, and sometimes less so. It might be that there was a change in the velocity distribution, that could be the case, but quite often it's more likely the window auto scales on the maximum and minimum velocities that it actually sees, and it applies the colours based on that particular measurement. So sometimes it biases how it actually looks. So if you want to change that, if we set in manual, so all I've done is I right clicked in there, set in manual minimum and maximum. So what was that maximum? I just look at what the maximum velocity was, 0.53 on that one. See, that is 3.7. I just say 1 and 2. Okay, and now what we've done is we have set the maximum velocities. Okay, so everything is now to exactly the same scaling. We've got 0 to 0.7. I'll change that again. Double left click. Take it down a bit, 0.7. So now the velocities that we're seeing are more related window by window. That helps me when I'm doing my quality control checks in just sort of seeing, okay, does the velocity distribution look about right each time? So you might, at the very end, we did a very quick measurement. Okay, where we
So instead of getting the maximum value, you set the
sorry, say we take it again.
maximum value.
So when I'm doing the visual check on the data, because I've now set the scalings of the velocities the same, I can sort of just quickly look and say yes. So all the velocities look like they are consistent. Okay, and it's one of the, you know, if they're not consistent, you then start to say why are they not consistent? Is it down to bad bottom track? Is it, you know, a bad track reference? Okay. So, you know, most of these, they look, there's a very slight difference in velocity distribution. This one looks very different, but this is the one where we went across in 34 seconds. Okay. Our duration of our measurement was 34 seconds. Whereas the other ones, you know, we went 3 minutes 15. Okay. Go back to this one. Just trying to see why we had that bad velocity there. Could be, it's just really picked up a bad velocity reference. It's where we started at the edge. The boat was probably pointed in this direction, and as we pulled it across very quickly, it's too quickly moved across, and it's not worked out the velocity component very well. So in reality, I would never be using that file anyway. It was just us to do it, see how fast we could do a measurement. The important ones are these. So now what am I looking for? I then look, we know we had RTK GPS. I look to see how the alignment of the track from the bottom track and the GPS look. Okay, so in this one, you know, I have the two plotting on there. They're almost identical. You know, so that's excellent. I can add in the VTG, and again, they're pretty much overlaying. If I go Control Tab now, and I'm looking in the middle window, looking at the tracks, bit of difference there on the VTG. Not too bad. The VTG data is slightly worse in all instances. I don't know why. I can't. If we're thinking about looking at the GPS data, if I go to the time series tab at the bottom, so the one next to Transit, I just have a quick look at, you know, I've got the number of satellites and the H dot being plotted here. I don't want H dot to be any higher than 2. That's my choice. The manual says 5. I say 2. So on that, I can do a right click there. I can do manual. I can say maximum 2. Okay, and then I know if anything goes up out of that scale, then I don't want to be using that data. So now I've got that set as there. If I Control Tab through these ones, I can quickly just see, okay, yes, all of them, my H dot value is good throughout. The one thing we do see is the number of satellites does change. The number of satellites we saw, not massively. The worst we ever saw was 7. Okay, so we were always using either 7 or 9, between 7 and 9 satellites for our data.
Different versions of the software shows the difference.
As I said on the previous one, on Transit, okay, you can change what parameter you have. If you go to the time series, on every individual, on all of the, what have we got, 5 profiles here, 5 graph. If you right click, left axis, you can actually change what value you look at in those, on each of those graphs. And this becomes a matter of preference, how you want to look at the data. So, Mark, can you just get rid of spam? No. The version you've got, having just freshly loaded it, you will have the default values that come up. Okay, so you have. This is my choice. These are, I always like to look at the pitch and the roll. A number of satellites and the H-dot. We actually changed this one yesterday while we were talking about water profiling code and bottom track mean contrast. I normally use bottom track mean contrast just to sort of see why we might have had a bottom track error. In the next one up, I always have the boat speed and the boat speed against the water speed. Okay, so that ideally we want the boat to be going at or below the speed of the water. Okay, so if we've got that, all of that, the bar graphs stay green. If we go a little bit too fast, it goes amber. And if we go much too fast, it goes red. Okay, and in the top, again that's where we changed that yesterday. So that's not the default I would normally set it up as. But the key thing is if we're looking at whether the GPS data is valid or not, is satellites and H-dot. I would definitely recommend you set up like that.
有没有问题？听得懂的举手。有 follow， 你有 follow 到同一个档案吗？你可以跟大家用中文解释一下吗？
先把它的坐标，左边的坐标、右边的坐标改的跟它一样，就是按在那图上面按右键，然后就是可以选择左边的坐标轴或右边的坐标轴。然后就是比如说第一个好了，第一个的话就要把就是选左边坐标轴，然后把原本的改成它的 track reference， 然后右边的也是这样做。然后每个图，我现在每个都改的跟它一样。
I like to, on the top one, I don't normally have track reference code being shown up there. I normally have bottom track depth and vertical beam depth plotting together. Bottom track. So we can quickly visually see the difference between the two and how make our decision as which one is the best one to be using for the depth measurement. The thing to remember about these windows is it's only the in-transit data that is shown. We do not show any of the edges data in here. Edges are shown in the next tab along at the bottom. So I'm just sort of going to scan through, and with these depths, you can see that the vertical beam depth is just a little bit noisier, but we're picking up more of the individual rocks that are on the bottom, whereas when you're using the 4-beam, the bottom track depths, it's taking the average of the 4 beams, so it tends to smooth it all out. On these measurements, it makes very little difference as to which one I'll be using. So this setup we now have back on screen. This is what I would normally have. Okay, I have the bottom track mean contrast. So that's looking, it sort of gives an indication of whether the bed is hard or soft, or how it changes. And then I have the speed of the water in the last cell. Okay, so if that goes up quite high, and we have sort of the contrast is quite low. Okay, so the difference between the water and the bed is quite low, and you see high velocity. The possibility of a moving bed increases. And so that helped me just make a few decisions on that. Another thing, if I just go back to the smart page, we should check as well that nothing has actually changed in any of these. That, you know, so the transducer depth is all 0.8. Everything's the same in there. You see that magnetic declination is green on mine at -3.9. That is because that was put in afterwards.
Yes.
So it makes a note to the person processing the data or looking at data, somebody has made a change. Okay, it's not as it was collected in the field. So having looked through that data, let's find. This is probably the worst one of those. We just
The file name is
is the one that ends 2833.
2S33.
Yeah.
Okay.
And why I say it's the worst one is if I just I'm just using the up arrow key to go back profile by profile. And if we have a look in this one, in this here, we have, in this profile, we have 18 cells of data being shown. And we go to the next one. We have 2 cells of data being shown. In this profile, it was using HD or pulse coherence. So if you look down in the SNR plot, down in the bottom left corner, you'll see it says SNR 3 megahertz HD. And if I go to the next one,
How do you
back,
go to the next one?
up arrow and down arrow,
Arrow down.
up arrow, down arrow, moves you up and down
Okay.
through
Okay.
one at a time.
Mhm.
If you do, let me just check. Control and up down takes you through 25, I think, at the time. And shift and control up and down takes you through 100 at a time. Okay. If you want to go all the way to the end, right arrow, all the way back to the start, left arrow. Okay, so the reason we've gone from having 20, whatever it was, 18 cells to 2 and 1, and then back to 12 cells, is that it was switching between high definition pulse coherent data and low definition pulse incoherent, or otherwise known as narrowband data. So that is narrowband data, that is pulse coherent data. Yeah. Yep. Mark's just putting that on the screen. It's a little graphic that shows how the instrument actually changes its processing based on water speed and water depth. Okay, so if the water depth is less than 40 centimetres, okay, I'm sorry, is that right? No, 1.2 metres, isn't it, Mark? Yeah, water depth less than 1.2 metres and water speed less than 0.4 of a metre. It will be using 3 megahertz pulse coherent data at 2 centimetres each cell. As we go deeper, at the same maximum water velocity, it will change the 2 centimetre cell to be a 5 centimetre cell. If the water speed then goes up above 0.4 of a metre per second, it will switch to pulse incoherent mode, okay, which is otherwise known as narrowband. And that's where we will then lose the resolution of the data. We don't so much lose the accuracy, but we certainly lose the resolution. Okay. With pulse incoherent data, we are taking the mean of, I don't know, it depends on speed and depth, but let's say somewhere about 50 hertz. When it's in pulse coherent data, we're taking, we're probably pinging it, I can't think what it is, Mark, it's much lower, it's around about 4, 9, again, depending on speed, somewhere between 4 and 9 pulses per second.
And that's usually because it's shallow water.
Shallow water, yeah.
So deeper water, you can get away with more pings. The shallower the water, because the reflection, that's another reason why it's...
It is.
Yeah.
That's if the water depth, so I'm sure this graphic's wrong now. Maybe I'm misunderstanding. It will switch to 1 megahertz soon. I think this graphic's wrong.
This is from Makata.
What the instrument tries to do, it always tries to use pulse coherence.
Right.
Okay, that's where we get the highest resolution data.
So if we're in 3 megahertz and we're operating at 3 megahertz,
Yeah.
on the 1 megahertz transducer is a broadband signal that sends out the signal to check. Do I switch or do I keep 3 megahertz? Is that,
Yes.
that's
Every second it's making that decision. Okay.
in a broadband
In a
signal.
broadband pulse.
So it could be in pulse coherent 3 megahertz, 3 megahertz, and on the 1 megahertz it sends out a broadband signal to check and makes a decision to keep it or to move into the.
But if it can't use 3 megahertz pulse coherent, it will then go to 1 megahertz pulse coherent. Okay, it won't go 3 megahertz pulse coherent, 3 megahertz incoherent, and then 1 megahertz pulse coherent. It will go 3 megahertz, 1 megahertz in pulse coherent, then it will go back to 3 megahertz pulse incoherent, and then to 1 megahertz pulse incoherent. Okay? The maximum depth you can work at in pulse coherent is around about 5 meters in pulse coherent. Okay? And the maximum water velocity you can operate pulse coherent in varies on depth. That's the problem with that one. It's somewhere between 0.7 of a meter per second and 1.2 meters per second. Okay? Above that, it will always be in pulse incoherent. The good news about that is once the velocity is going that fast, actually we don't need that resolution Okay, to be able to see the structure of the water so well. Okay. Slow-moving water is by nature more turbulent, and this has more variability in it than fast-moving water. Something else you'll just see on, you won't have this on your, because you're using 3.5 software. So with the new compass, I was saying how it reports in real time any potential errors being brought about by magnetic interference. You see here, we get the dotted line always being plotted. That's at the 3.5% error margin. Okay. We see here that we have 7 instances of where that has been exceeded. So it's saying that there could be some magnetic interference in the channel that is affecting the compass. If I just tab through each of them, it wasn't always the same. No, sorry, it's got a full file there. That's okay. I was only looking at a partial bit of the file. Okay, so you see it's only occurring on the left bank at the very beginning.
6 points.
Yeah. Okay, so there's not many. So that's because as we got close to the edge, there was probably maybe a pipe there, maybe there's some reinforcement in the bank or something like that. Iron in the bank. Okay. It's having on this one, it's having very little effect. It's only just over what we say is the recommendation. 3.5 at this 3.5% equates to about 2 degrees on the compass, and 2 degrees is the specification on our compass, on the accuracy of the compass.
So it's acceptable.
That's acceptable.
Okay.
No problem at all with that. But you'll also see here how the magnetic error varied across the channel. So although it's always acceptable, you'll see that the background magnetic fields were quite variable across that channel. But less than 3.5.
I'm curious about the depth measure by pattern track. You see that in the middle of the channel, the depth almost shallow.
Yeah, okay.
Either in the left hand side or the right hand side.
Yeah, so that was on the left hand bank. On the left bank, it was deeper. Yeah.
Why?
You would think in a straight channel that it would stay, but I reckon it's at high velocities because of the bend upstream.
Mm-hmm.
So we had a nice straight channel, and they were saying it was deeper in this section down here, but maybe sort of the bend sort of coming from here. As the water velocities come round, the fast water always goes to the outside of the bend, and then it's probably deflected off over to this side, and it started scouring this out. That's why I always think we have deeper water there.
Oh.
So as the water's hit this, as it's hit this bend here, it deflects across. I would guess that's why that's happening.
This is why the flow depth in the near the left bend is deeper.
Yeah.
Okay.
Sorry, I don't know. I'm guessing, but I've seen it. I've seen it
have
before.
a photograph, air photo of it.
It might be, yes.
Yeah.
I don't know. If anybody's got internet connection and got Google Earth or something like that, to have a aerial photo or satellite photo of the site. Okay, we'll come back to that. Yep. Okay. So also we see that we're
The first one, we check the compass quality.
compass quality. Yeah, we've so by looking at the data, we're seeing that there's no deviation between the two in general. So the compass is good.
Mm-hmm.
I could have, if I wanted to, go back to Smart Page.
Smart page.
Yeah.
Okay.
And then where it says compass calibration, I can open that.
Open.
Yeah.
Okay.
And if I click, oh, you won't have it on yours because this is.
No, that's a new one. I use it.
Oh, okay. And then I go view.
Oh, view?
Yeah.
Okay, pick one.
Pick one, and then I go compass cal. And we did 2 compass calibrations.
Yes.
The second one was good, the first one not so good. So we'll look at the
Second one.
second one. That's yeah. 1102.
Yeah.
And this is that. So here we see.
Oh. Yeah.
Okay.
The circle very tight.
Very tight. If
Yeah.
I view the first one now.
Okay, so view the first one. Oh.
Okay.
Not so good.
Not so good.
So then for the
So we could see actually from this, if we know our earth ball of the site, we could actually tell where the interference was coming from because it was occurring from around about 170 degrees through to 5 degrees. Okay, so we could work out exactly where it was. It actually works as a really good metal detector.
Actually, because you can plot the time series for magnetometer, right?
You could.
So you can actually, yeah. We were just talking about
So-
the water book.
So we can use this to check the compass calibration.
Yeah, just to check, just look at and visually see how your compass calibration makes.
Okay.
There's not a lot in there. We talked about, if you read at the bottom, it's sort of a few considerations or